Okay, do we have any questions before we get started? Okay, all right, so I want to point out um, the videos from last week are under stream videos, and um, this week one stuff has your chemistry primer in it, which you were supposed to be doing, and introduction to mastering if you want to do that. And that was due over the weekend, so I haven't checked to see how many of you did that yet. I'm going to probably move this week one module to the end. It'll still be here, but it'll be probably at the end, and then have week two up at the top. So right now we're working on chapter 6, which has us in line with what we're supposed to be doing for week 2, but notice your problems are due Sunday. So I wanted to stay a little ahead on our chapter completion. I'm hoping to complete chapter 6 today and move on to chapter 12, which is our next chapter, which is here, okay? So let's go ahead and get started on finishing chapter 6. We're about 2/3 of the way through it. Chapter 6 is pretty long, but chapter 12 is quite a bit shorter, so I think we'll be able to complete chapter 12 by the end of this week. Okay? Right. Let's see here. Chapter 6, gases in chemical reactions. Okay, so our next topic is talking about gases that are evolved during chemical reactions. So one of the types of reactions we looked at last semester was evolution of a gas. So when gas is evolved in a chemical reaction, so in other words, if you have, say, I don't know why my drawing thing gave out, stopped working in the last class I was in. I guess it's working again now. So if you have a test tube that's evolving a gas where you've got a reaction going on, okay, you can capture that gas. Okay, usually that's done underwater. Okay, and you can measure that gas, and from the volume, you can basically get the number of moles of gas that was evolved. You can measure that because you've got it under, say, water, and you're collecting the gas. You can measure the volume of gas collected, and that can give you the number of moles you collected. So you can use that relationship in order to compare to the number of moles of substance that you started with. So we can do some stoichiometry with this in order to give us the amount of our, say, starting material, or the amount of what fully reacted in a reaction. So from the number of moles, we can basically get the volume of the gas that was um, evolved, or from the volume we can get the number of moles and that sort of thing. So let's look at how, well, we'll look at how that's done in a few minutes. I'll probably come back and do some calculations at the end. Right, and so we can also use partial pressure if we're just considering one gas, if we want to be measuring that. When gases are at standard temperature and pressure, 1 mole, remember, is 22.4 liters. And so if we have mass A, we can convert that to moles of A, and then moles of B, and then we can get mass of B, and so forth. If we have pressure, volume, or temperature of gas A, that can give you pressure, volume, and temperature. That can give us the amount in moles, and then we can convert that to moles of B and get some unit for gas B. Okay. So these get a little complicated, but if you kind of understand how the overall thing is working, then it's not too bad. So basically, we can say how many grams of water form when 1.24 liters of hydrogen gas at standard temperature and pressure completely reacts with oxygen. Okay, so basically we've got volume here, and we're trying to convert to grams of water. Okay, so how many grams of water form? So this is what we're forming here. When 1.24 liters of hydrogen gas, so we've got, and this is in the gas phase. All right, and so when 1.24 liters of hydrogen gas in the gas phase reacts completely with oxygen, we don't really need to know the oxygen because we can go uh, grams to moles. I'm sorry, we got volume here. So we can go volume to moles and then moles of hydrogen to moles of water. Right. So is this a problem over here? Hold on just a second. I think I'm going to go ahead and save all the problems for the end. So I'm going to go ahead and come back to this later. Okay. I'm going to work some math problems at the end. Okay, so nitrogen and hydrogen react to form ammonia according to the following equation. So this is a different kind of concept here. Nitrogen gas reacts with hydrogen gas to form NH3 gas. So here we have nitrogen and hydrogen, N2 and H2, and they're reacting to form this ammonia. Okay, so they're forming ammonia. Okay, so if the volume is kept constant and nothing is added to the reaction mixture, what happens to the total pressure during the course of the reaction? So notice that we're reacting a mole of hydrogen and a mole of nitrogen and 3 moles of hydrogen to give us 2 moles of ammonia. So we've got 4 moles of gas going to 2 moles of gas. So what is that going to do to the pressure? The pressure is going to decrease because we're decreasing the amount, the number of moles of the gas. All right, so kinetic molecular theory. So I'm going to just run through the rest of this theory real quick and then we'll work some problems. So the simplest model for the behavior of gases is kinetic molecular theory. Gas is a collection of particles, and we can think of an ideal gas as not interacting with anything around it, okay? And these are all going to be in constant motion. So their kinetic energy is basically going to depend on temperature. So we make some assumptions here that the size of the gas molecules is negligible because they're so far apart. It really doesn't matter. The average kinetic energy of a particle is proportional to the temperature in Kelvin, okay? And the collision of a particle with another is completely elastic. So they're not losing energy, okay? Um, so when the moving gas particles hit another particle or the container, they don't stick to each other but bounce off and continue in another direction. And we also assume that there is a lot of space between these gas particles, okay? So the average kinetic energy is directly proportional to temperature because temperature is a measurement of energy. So if you raise the temperature of the gas, the average speed of the particles is going to increase. But they're not all moving at the same speed. Some are going to be going faster and some are going to be going slower. So just the average speed of the particles is going to increase, okay? So the collision of one particle with another is completely elastic, which means that they may exchange energy, but there's no overall loss of energy, okay? So any kinetic energy lost by one particle is completely gained by the other particle. So in an elastic collision, if they bounce into each other, we don't lose energy. They just transfer the energy to one another. Whereas an inelastic collision, which is what we view on the macro scale, some of the energy is going to be lost due to heat or noise or whatever. All right, and so we're going to look at some calculations with average kinetic energy in just a little bit, okay? All right, so pressure is equal to force over area, and this is not a calculation that we really do in this class, but basically this force is what keeps a balloon inflated. It's the pressure of the gas again, colliding with the walls of the container or of the balloon and that sort of thing. So Boyle's law states that a volume of a gas is inversely proportional to pressure, so decreasing the volume forces the molecules into a smaller space. So that's going to increase the pressure. Okay, Charles's law states that the volume of a gas is directly proportional to temperature because, according to kinetic molecular theory, when we increase the temperature, the average kinetic energy increases. So that's going to increase the volume because we're going to have more collisions with the walls of the container. Avogadro's law states that the volume of a gas is directly proportional to the number of gas molecules. So if everything else stays the same, and we already talked about this before, then if you increase the amount of gas you have, it's going to increase the volume. All right, Dalton's law says the total pressure of a gas mixture is the sum of the partial pressures, okay? So in other words, the total pressure is the sum of each individual pressure of each individual component of a gas mixture. All right, so kinetic molecular theory is a quantitative model that implies that PV is equal to nRT, which is our formula that we've used a lot before. So the pressure on a wall of a container occupied by particles in constant motion is the total force on the wall due to collisions divided by the area. And again, we don't really use this formula at all. It's just kind of a concept that we talk about, okay? All right, so we have this formula here, and I don't really want to go through the derivation of this, but the average, the root mean square of basically the kinetic energy is equal to 3 times the gas law constant times temperature divided by the molecular weight, okay? So the energy is proportional to temperature, okay, divided by the molecular weight. So lighter particles will have a faster average velocity than more massive particles because the larger the molecular weight, the slower they're going to move in order to keep that constant average velocity. So this nu stands for average velocity. All right, so how does the approximate root mean squared velocity of neon compare to that of krypton at the same temperature? So let's look at our periodic table here. Where is it? That wasn't what I wanted. Periodic table, here it is. So we've got neon versus krypton. Notice that neon is about 20 and krypton is about 80. Okay, so the root mean square velocity of neon is approximately 2 times that of krypton, okay? Because krypton is heavier. So if we look at molecular speed, the root mean square velocity, versus molar mass, what we see is that lighter particles have a higher average velocity. Okay, so that's that new RMS. Okay, so our average velocity is going to be right here in the middle of these peaks. Okay, so for O2, in fact, I probably should draw this in that color. For O2, we've got our average velocity being right here, and N2 is heavier, so we'll go with purple. The average velocity is going to be further up. It's going to be higher. Lighter, so the average velocity is going to be further up. It's going to be higher because the lighter particles have a faster velocity, okay? Water is in the blue here, and it is lighter, so it's going to have a faster average velocity. And then helium is even lighter. So it's going to have that their average velocity is faster. And then hydrogen, the average velocity is about right here. So it's going to be even faster. So the faster particles have a faster velocity. Because of this formula, the velocity is proportional to the molecular weight, okay? All right, and so notice that the average velocity is also proportional to temperature. And again, I don't think we're going to be using any of these other formulas here, but you'll notice that the original formula was nu RMS, so the average velocity is equal to the square root of, let's go back up, RT over M, okay? The square root of 3 RT over M. where M is the molar mass. And remember, molar mass is in grams per mole, right? So if you multiply by, in other words, if you use Avogadro's number and the mass of the particles, then you can actually convert to Avogadro's number times the mass, okay, and that's going to give you the molar mass. So we can get this other formula here where we've got the the average root mean square velocity is equal to the square root of 3RT over Avogadro's number times the mass. So instead of the molar mass, we can just use the mass times basically the amount. So Avogadro's number would give us the amount of a mole times the mass. So it's kind of the same thing. All right, and so as the temperature of a gas increases, okay, the velocity distribution of the molecules shift toward higher velocity. So we're talking here about nitrogen. So molecular velocity is going to increase as temperature increases the average velocity. Now some of those are going to be going slower and some are going to be going faster, but the distribution is going to spread out at higher temperatures, okay? So which of these ideal gas samples has the greatest pressure? Remember, volume is negligible, so this is kind of trying to trick you here. So the one with the higher pressure is going to be the one with the greater number of gas particles, even though they're smaller, so that would be C, because they're so far apart that their volume is essentially negligible, okay? All right, so mean free path, we're going to use this to actually help us do a calculation. And so our calculation is going to be, we're going to be able to calculate the molar mass of a gas from this. So let's back up. I wanted you to kind of see where we're going with this. The mean free path says that molecules in a gas travel in straight lines until they collide with another molecule or the container, okay? The average distance a molecule travels between collisions is called the mean free path. The mean free path decreases as the pressure increases, which kind of makes sense. They're going to be more likely to bump into each other. So we have these two different topics that kind of result from this, or that segues into diffusion and effusion. The process of a collection of molecules spreading out from high concentration to low concentration is called diffusion. We're not really going to be doing anything with that. But the process by which a collection of molecules escapes through a small hole into a vacuum is called effusion. Okay, so diffusion is like if you have a perfume sample in the side of a room, okay, it's going to be more concentrated when you first release it, and then as it spreads out, okay, it's going to tend to spread out because it's going to go from areas of high concentration to low concentration. So a few minutes later, you're going to be able to smell it here on the other side of the room. Okay, that would be diffusion. Okay, so effusion says that molecules can escape through a small hole into a vacuum where the sample doesn't exist. So if you've got a chamber and one of those sides has nothing in it, and then you open a hole up and you've got your sample over here on one side, okay, it means that you open this hole, the sample's going to start going over to the other side, okay? The rate of diffusion and effusion of a gas are both related to its average velocity, okay? So for gases at the same temperature, this means that the rate of gas movement is inversely proportional to the square root of the molar mass. So we get this ratio. We'll look at that in a minute. So if you have an evacuated container that has nothing in it and you have a gas over here on the other side, and you open a hole, the gas is going to begin to go from the side of high concentration to the vacuum side, okay, over to the side that had nothing in it. So we can get this ratio here, the rate of effusion of gas A. So what we're saying here is that we have two different gases. So we have this gas, okay, we have two different gases in the container, and then we have another gas, okay, two different gases. And those gases are going to have two different molecular weights, okay? So the rate that that A moves into the other container, A is in blue actually, is going to differ from the rate that B moves into the other container, and both of those rates are going to be dependent on the molecular weight of one to the other, okay? Now, of course, their average velocity is going to depend on temperature, but since they're both at the same temperature, this is going to factor out. So the rate of effusion for A divided by the rate of effusion for B is going to be equal to the square root of the molar mass of B divided by the molar mass of A, okay? So we're going to do some calculations for that. We're going to actually be able to experimentally determine the rate of A and the rate of B, okay, and then we'll have the molar mass of one of those, okay. That'll allow us to calculate the molar mass of an unknown gas, okay. So this is molar mass of an unknown gas. We're going to do some of those in a minute. Again, I don't want to swap back and forth between working problems and discussing the slides because I end up getting bogged down in the slides and not getting enough problems done. So I want to be able to finish this up. So a glass tube contains an equal number of moles of helium and argon. After 5 minutes, half the particles escape through a small hole. What are the relative amounts of helium and argon in the tube at 5 minutes? So the tube has to contain a greater number of moles of argon than helium. Half the particles escape through a small hole. What are the relative amounts of helium and argon? Helium and argon. Oh, okay. I see what they're saying here. So a glass tube contains an equal number of moles of helium and argon. Okay? Helium and argon. And then we open a hole. All right, so after 5 minutes, half of the particles escape through a small hole in the glass. Okay, so we had an equal number of helium and argon in here. So after 5 minutes, how much are we going to have left? We're going to have more argon left because helium is smaller and it's going to escape faster from the tube. Okay. All right, I'm going to go ahead and discuss real gases real quick, but we don't actually work any calculations with these in this book. Now, in some general chemistry classes, you would work these calculations, but we don't do them in this book, okay? So real gases often don't behave like ideal gases. So remember we made these assumptions that they have no attractions between the gas molecules, that the gas molecules essentially don't take up any space because there's so much distance between them that the space they actually take up is negligible. Okay, so at low, very, very low temperatures and very, very high pressures, these assumptions are not valid. So remember, molar volume for an ideal gas is 22.4 liters per mole, right? So an ideal gas is 22.41 liters per mole, but you can see here that for real gases, okay, we can see that for like chlorine, it's 22.06 liters per mole, CO2 22.31. So I'm not sure of the actual conditions here, but they vary a little bit. Real gases are going to vary a little bit from these conditions. Okay, and especially at very low temperature and very high pressure, we're going to see that because as the pressure increases, the molar volume is going to be greater than that of an ideal gas. Okay, so at very high pressure, the argon is going to occupy a significant volume. So as you push these things together, they're going to start interacting with each other, and we're going to have to start accounting for the differences from that ideal gas behavior. So at high pressure, volume is higher than predicted, okay, because it starts to actually matter. So at high pressure, these things actually start to take up space that we have to account for. Okay, I'm not going to go into a lot of detail again without this. And so the way that we account for that is a different term that's different for each gas, okay? And then at low temperature, we're also going to see a deviation from ideal gas behavior. So for xenon, it would have looked like the red line, but it looks more like the green line, okay? So we have to account for that as a different little unit in the equation, different part of the equation. So we have this equation for real gases. Instead of PV equals nRT, we have P plus some intermolecular forces term times V minus this particle volume term equals nRT. Okay, so basically it's a correction factor for the pressure and the volume at as we reach higher pressure and lower temperature. Okay, I gotta admit somebody here. See the person? Did the person get admitted? I don't know. I don't know. Anyway, okay, so I'm not going to go into that since we're not actually doing these calculations, but ideal gases differ from real gases at significantly at higher pressure and lower temperature. That's basically what this means, okay? All right, so I'm going to stop here and work some problems. So remember we were talking about gases and chemical reactions. So we're going to go back and work some of those. Then we're going to do the average kinetic energy problems, and then we're going to do some diffusion problems. So basically, I think 3 different types of problems here, okay? So remember that if we have like a mass of A, we can convert that to moles of A in a chemical reaction, and then using our balanced equation, we can convert that to moles of B from the chemical reaction and the mass of B. Okay, so we can get those values from basically knowing volume and knowing number of moles, depending on the conditions. Okay, so let's read this problem. Methanol can be synthesized by this reaction. Okay, carbon monoxide plus hydrogen yields methanol. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury is needed to synthesize 35.7 grams of methanol? Okay, so we're going to start with what we were given, which is 35.7 grams of methanol, and then we have to convert that volume to volume in hydrogen gas. So how are we going to do that? Okay, so we're given grams of methanol, our temperature is 355, our pressure is 738 millimeters of mercury. Remember, our R is equal to 0.206 liters atmospheres per mole Kelvin, right? And so we need our units in liters, atmospheres, moles, and Kelvin, okay? So our temperature's in Kelvin, but we need our pressure in atmosphere, and we need to convert this grams to moles, okay, in order to do these calculations. So from grams of methanol, we can get moles of methanol. From moles of methanol, we can get moles of hydrogen. And from moles of hydrogen, then we can get, and the pressure and the temperature, we can get volume of hydrogen, okay? So from grams of methanol, we get moles of methanol through the molecular weight of methanol, which is 32.04 grams per mole, which you could have added up from the periodic table if you had to. So actually, you'd have to do that here, wouldn't you? Yeah. So the periodic table tells us that carbon is 12.011, hydrogen is 3 times 1.008, and we've got 4 hydrogens, I'm sorry, 4 times 1.008, and we've got 1 oxygen, which is 1 times 15.999 or 16.00, and that should give us 32.04 grams per mole, okay? And then we can go moles of methanol to moles of hydrogen from the molecular formula. We've got 2 moles of hydrogen is 1 mole of methanol, okay? And then when we get moles of hydrogen, we can convert that to volume of hydrogen from our PV equals nRT formula. Okay, so let's go ahead and work that problem. Let's write some of this stuff down. So we've got 32.04 grams per mole. That's our CH3OH. Okay, we've got T equals 355 Kelvin. Pressure equals 738 millimeters of mercury. Okay, and then our molecular formula, our balanced equation tells us 2H2 to 1 CH3OH. And then, of course, we got our formula, just write that here. PV equals nRT. So this is a fairly complicated problem. Okay. So let's go ahead and work this. All right, we started out with 35.7 grams of methanol. All right, and that's 32.04 grams is 1 mole, and that gives us 1.1142 moles of CH3OH. Okay, so we had three sig figs, so we'll put a line there. All right, and we can convert that moles of methanol to moles of H2 using this relationship here, okay, from the balanced equation. So 1.1142 moles of CH3OH. Sorry about the gunk here. I keep touching the tablet. And then 2 moles of H2 is 1 mole CH3OH from the balanced equation, and that's equal to 2.2284 moles of H2. Okay. Now we need to convert pressure to atmospheres, so we'll go ahead and just do that here. All right, so 760 millimeters of mercury is 1 atmosphere. Okay, so that's equal to 0.97105 atmospheres. Okay. All right, so we know that PV equals nRT. I'm trying to get volume, right, because I've got moles of H2 already. I need volume of H2. Okay, so if I use the moles of H2 and everything else, I should be able to calculate that. That's going to be equal to, okay, nRT over P, which is equal to 2.2284 moles of H2 times 0.08206 liters atmospheres per mole Kelvin times temperature, which is 355 Kelvin, divided by pressure, which is 0.97105 atmospheres. Okay, so atmospheres cancels, moles cancels, kelvins cancels. Now we're left with liters, which is volume, so that's correct. And that gives us 66.9 liters. Okay. All right, so you do have to think about these problems a little bit in order to plug them in. Okay, so let's do the next one, which is 6.12. Okay, so in the reaction shown here, 4.58 liters of O2 forms at pressure equals 745 millimeters of mercury, T equals 308 K. How many grams of silver dioxide decomposed? Okay, so we've got 2 moles of silver dioxide, okay, gives us 4 moles of silver plus 1 mole of oxygen, okay? So we're evolving 4.58 liters of oxygen, okay? So we want to know how many grams of silver dioxide decomposed, okay? So from the volume, okay, we can get number of moles of O2. And how is that? Remember, PV equals nRT. So we've got the volume, okay, and that was given here. We've got the pressure, which is here. We've got to convert that to atmospheres. We've got R, and we've got the temperature. So from that, we can get number of moles of O2. Okay, and then let's write that down. So from the volume, we can get moles of O2. Okay, and then from moles, and that's given from the volume here. Moles of O2, from moles of O2, we can get moles of Ag2O. That's from the balanced equation, okay? And then from the moles of silver dioxide, we can get grams of silver dioxide from the molecular formula, for the molecular weight, okay? All right, so let's go ahead and convert everything now. So let's say 745 millimeters of mercury. All right, 760 millimeters of mercury is 1 atmosphere. So that is equal to 0.980263 atmospheres, okay? And now we got temperature. All right, the other thing we need is the molecular weight of silver dioxide, right? If you look that up, so how would I do that? I would take 2 times the molecular weight of silver plus 1 times oxygen, and it turns out that's 231.8 grams per mole. If you don't remember how to do that, meet me during office hours and we'll go over that. I don't want to spend a lot of time on that. So let's go ahead and work this. So moles of O2, so PV equals nRT, so N is equal to PV over RT, right? So N is equal to PV over RT is equal to the pressure, which is 0.980263 atmospheres times 0.08206 liters atmospheres per mole Kelvin times the volume, which is 4.5. Go ahead and erase this. 4.58 liters. Wait a minute, I'm supposed to divide by R. Sorry, guys. All right, PV, which is volume, is 4.58 liters, divided by R, which is 0.08206 liters atmospheres per mole Kelvin. And I like to keep all these units because it'll help keep you straight on whether you did this right. Because if your units don't cancel, you probably did something wrong. And temperature is 308 K. Okay? And that is going, so liters cancels, atmospheres cancels, kelvins cancels, and we're left with moles, which comes back to the top. And that's going to be 1.77634 moles. And this was volume of O2, okay? So that's volume of O2. So that's going to give us moles of O2. So that's moles of O2. So we don't have moles of silver dioxide yet. So we've got 1.77634 moles of O2, and we've got 2 moles of Ag2O to 1 mole of O2. That comes from the balanced equation, okay, 2 to 1. And then we can use the molecular weight and just go straight through. 231.8 grams of Ag2O to 1 mole of Ag2O equals 82.4 grams of Ag2O. Okay, so that's how many grams reacted to, to give us our oxygen. Okay, so let's see if we want to do this one. In the previous reaction, what mass of Ag2O in grams is required to form 388 milliliters of oxygen at this pressure and temperature? Okay, so that's 6.12 more practice. All right. So we got the same balanced equation. So we're still forming oxygen. So that's a 2 to 1 ratio. Let's just write that down. 2 Ag2O to 1 mole of oxygen, okay? that we want mass of silver dioxide. Okay, so we've got 380 milliliters of oxygen. So 388 milliliters, 1,000 milliliters is 1 liter. That's 0.388 liters of oxygen. Okay, our pressure is equal to 734 millimeters of mercury. So 760 millimeters of mercury is 1 atmosphere, and that's equal to 0.965789 atmospheres of O2. Okay, that's the pressure of oxygen. All right, the temperature is equal to 25.0 plus 273.15, because we got to go to kelvins, is 198.15 Kelvin. And the volume, we already did volume. The volume is equal to that, right? All right, so what are we going to do? We got PV equals nRT. All right, so moles of O2 is equal to pressure times that's the partial pressure of O2, times the volume of O2, divided by R times the temperature, which is equal to 0.965789 atmospheres, that's the partial pressure of O2, times 0.388 liters, divided by 0.08206 liters atmospheres per mole Kelvin, times 298.15 Kelvin equals 0.01536161 moles of O2. But our question was what mass of silver dioxide. So we got, I need more room here. All right. I'm going to have to keep writing down here down the side, okay? So I've got moles of O2, okay, and I'm going to 0.01536161, that's moles of O2, and I've got 2 moles of Ag2O to 1 mole of O2, okay? And then I'm going to multiply that. So I'm going to bring that down here, multiply that times 231.8 grams of Ag2O per mole. Okay, so this is multiplied times that. Hopefully you can see that on that. I ran out of room, sorry. Is equal to 7.10 grams of Ag2O. Okay, so that's grams. Yeah, that's what we needed. Okay, so I took the moles of O2, I got moles of silver dioxide from the balanced equation, and then used the molecular weight to convert that to grams of silver dioxide. Okay, so hopefully you guys can see that. Okay, so this one is worked kind of the same way. I don't know if I'm going to do this one. How many grams of water form when 1.24 liters of hydrogen gas at standard temperature and pressure completely reacts with O2? So the balanced equation, 2H2 plus 1O2 yields 2H2O. So we're looking for grams of water. So you're given it volume of hydrogen gas and asked to determine the mass of water. So given 1.24 liters of H2, find grams. Okay, so given liters of H2, we can use that 22.4 liters per mole to get moles of H2, then 2 moles of H2 to 2 moles of H2O from the balanced equation here, 2 to 2. Okay, and then from that we can get 18.02 grams per mole. Okay, so how are we going to work this one? I think I'm going to go ahead and just kind of skip through this one. Okay, liters of H2, 22.4 liters per mole, 2 moles of H2 to 2 mole. There's an error here. 2 moles of H2 to 2 moles of water. It still comes out the same, but they wrote it down wrong. And then we've got 18.02 grams per mole. That gives us 0.998 grams of water. So that one was fairly straightforward. Okay, so I'll go ahead and work this next one here since it's not worked out. How many liters of, that's 0.13, how many liters of oxygen at standard temperature and pressure are required to form 10.5 grams of water? Okay, 10.5 grams of water. So we've got oxygen and water. So we've got 1 O2 to 2 waters, right? So that's a 1 to 2 ratio. So 6.13, we're going to start with 10.5 grams of O2, okay? So we're going to convert that to moles of O2, okay? And how are we going to do that? We're going to use the 18.02 grams per mole, right? And then we're going to convert that to moles of, no, I'm sorry, grams of H2O. I did that. Sorry. So I've got 10.5 grams of water. So using 18.02 grams per mole, I'm going to convert to moles of water. Okay, and then I can go moles of O2 from the balanced equation. That's 1 mole of O2 to 2 moles of water. Okay, and then I can convert moles of O2 to liters. And that's what we wanted, 22.4 liters of O2 per mole of O2. That's supposed to be liters, okay? All right, so this is a straightforward calculation, so let's go ahead and get started. All right, so we've got 10.5 grams of water. All right, using the molecular weight, we've got 18.02 grams of water is 1 mole of water, okay? And then from the balanced equation, I've got 1 mole of O2 to 2 moles of water. So I'm just putting water on the bottom here because it cancels. So we want everything to cancel. Grams cancels, moles of water canceled, and we're left with moles of O2, okay? So now I know that 1 mole of O2 is 22.4 liters of O2, and that is volume of O2, which is what we wanted. So if I multiply 10.5 times 22.4 divided by 18.02 and the hit equals and divide that by 2, I get 6.53 liters of O2, okay? All right, so that would be stoichiometric calculations. So the next problem is going to be the root mean square velocity. So that was what I was talking about. We can get the average root mean square velocity if we know like the temperature and the molar mass. Okay, so you're given, calculate the root mean square velocity of oxygen molecules at 25 degrees C. Remember, we're using R here. That's 0.08206 liters atmospheres per mole Kelvin. So we need our temperature in Kelvin. Okay, so we're given that we need O2. So that's going to be the molar mass of O2. Okay, so what do we, let's write down what we know here. So the molar mass of O2 is equal to what? So O2, so oxygen is equal to 16 grams per mole. All right. So O2 is going to be 2 times 16, which is 32.00 grams per mole. Okay. All right, and the temperature is 25 degrees C, so that's 25 plus 273 is equal to 298 Kelvin. Okay, so we can calculate the root mean square deviation from that. Okay, RT over N. Oh, I completely forgot to mention this. All right, grams. We got to have that in kilograms per mole. Okay, I forgot about that. The molecular weight here is not in grams per mole. It is in kilograms per mole. Okay, and the R here is in joules per mole Kelvin. So we're actually using a different R, and we're using a different molecular weight kind of thing. So let's go back to our. I completely forgot about that. Let's go back to our PowerPoints. All right, it's not actually mentioned. Oh yeah, here it is. Okay. So R is the gas constant, but we're using a different gas constant here. We're using the gas constant in different energy units. So all this is it's been converted to joules per mole Kelvin. So instead of liters, atmospheres per mole Kelvin, we're going to use the gas constant in joules per mole Kelvin, which is 8.314 instead. Okay, a 1 joule is kilogram meter squared per second squared. So if you use that relationship, you can convert that R into this R. It's the same number, but we're using different units. Okay, and the molar mass is going to be given in kilograms per mole instead of grams per mole. So you have to actually convert that to kilograms per mole. Okay, so we have to use that conversion in order to do this. Okay, so I had completely forgotten about that. So our R is in fact going to be a different number. So that's 8.314 joules per mole Kelvin. Okay, and that's our R. And our molar mass has to be in kilograms per mole. Okay, so let's do that conversion. All right, so the molar mass of O2 is equal to, okay, 32.00. So that's 16 times 2 because we've got O2 and oxygen 16 grams of O2 per mole of O2. So we take the regular molecular weight. I meant just per mole here. That's good enough. All right, and then we say 1 kilogram is equal to 1,000 grams, right? So we can convert grams to kilograms, and that gives us 32.00 times 10 to the minus 3 kilograms of O2. So we can just do it in scientific notation per mole. Okay. All right, and so then we're going to use this R, so we can just plug everything in. The average RMS, so root mean square velocity, is equal to the square root of 3 times this R, which is 8.314 joules per mole Kelvin, times 298K, divided by our molecular weight in kilograms. So that's there's an error on this stupid sheet. 32.00 times 10 to the minus third kilograms per mole of O2. Okay. All right. So moles is both on the bottom, so that's cancels. Okay. Kelvin cancels. All right, and we're left with joules per kilogram. Is that right? Yeah. And so that is equal to the square root of, and they've got 5.66117 times 10 to the 4th, okay? And that would be equal to 238. Now, we also have this other conversion factor, and that says that 1 joule is equal to 1 kilogram meter squared per second squared, which is why we have to convert grams to kilograms, okay? And remember, these units were joules per kilogram, okay? So that's joules per, well, I need to do that before we take the square root, right? All right, and so if we convert that, we say, so a joule is a kilogram meter squared per second squared. So let's erase that and plug that in. Kilogram meter squared per second squared. So kilograms cancels. So when we take the square root, we're left with meters per second. Okay, so the answer is 238 meters per second because this is velocity. Okay. All right, so I'm sorry I kind of forgot about that. That's essentially how you do that kind of problem, and I had forgotten about the units, difference in the units there. All right. All right. And I actually wrote the number down wrong. 298, 32. I got this number wrong here. So that's really frustrating because I copied the wrong number. Right, so that is actually the square root of 202.32 times 10 to the 5th joules per kilogram. So that's kilogram meter squared per kilogram second squared. So that gives us 482 meters per second. So I'm sorry, I copied the number down wrong. But I had the units correct. All right, so I copied off of the wrong problem. All right, so calculate the root mean square velocity of gaseous xenon atoms at 25 degrees C. Okay, so the molar mass of xenon is equal to 131.293 grams per mole. Now remember, this is just Xe. Xenon is a noble gas, so it's actually just going to hang out by itself. So that's going to be 131.249, okay? Where am I at? Here. All right, and so we have to convert that to kilograms. So that's going to be, because we need that for the units, so it's going to be 1,000 grams is 1 kilogram is equal to 0.131293 kilograms per mole. Okay. All right. So the temperature is 25 degrees C. So that's equal to 298 Kelvin, just like we had in the previous slide. Okay. All right. So the new RMS is equal to the square root of 3RT over the molar mass in kilograms. And remember, our R is equal to 8.314 joules per mole Kelvin. And also remember that a joule is equal to 1 kilogram meter squared per second squared. Okay, so this is equal to the square root of 3 times 8.314 joules per mole Kelvin times 298 Kelvin divided by 0.131293 kilograms per mole, which is equal to the square root of 5.66117 times 10 to the fourth. And I'm going to have to move that down so we can see our units better. Okay, let me move that down here. Okay. All right, so that's equal to, let's do that again, the square root of 5.66117 times 10 to the fourth, and that is joules, because look here, kelvins cancels, moles cancels, we're left with joules per kilogram, okay? So I'm going to change colors here and say joules is now kilogram meter square per second squared. Okay, so kilograms canceled and we're left with meters squared per second squared. So then when we take the square root of that, that's going to give us 238 meters per second. Okay, so our root mean square velocity is 238 meters per second. All right, so the last problem we have is Graham's law of effusion. And we're going back to our molecular weight in grams per mole because we're not using that joule conversion that's kilogram meter square per second squared. So again, we have grams per mole. And so we know that the rate of the effusion of A, in other words, the rate of that gas. So we've got two different gas particles in a container. Let's go back to the theory. All right, now we put a little hole in the container between these two containers, and the other container over here is in a vacuum. So both the yellow and the blue, which would be A and B, are going to begin to go to the other side, and that's called effusion. The rate of the movement of A to the other side over the rate of the movement of B to the other side is equal to the square root of the molar mass of B divided by the molar mass of A. So what we know is the rate of the unknown divided by the rate of N2, which we know, okay, is equal to 0.462. Okay, so an unknown gas, it effuses at a rate, so in other words, this unknown gas, we don't know the molecular weight of it, that is 0.462 times that of nitrogen gas at the same temperature. Calculate the molar mass of the unknown gas in grams per mole. So what we could say is the rate, where I can write here. All right, the rate of the unknown divided by the rate of N2 is equal to the square root of the molar mass of N2 divided by the molar mass of the unknown, and this is in grams per mole, okay? So we want to know the molar mass of the unknown thing. So how do we do that? All right, we have to, is that right? Squared. I don't think they've got this correct. Okay. So what are we going to do? We're going to square both sides. So we've got to solve for the molar mass of the unknown, right? So how are we going to do that? We're going to square both sides. So we're going to say the rate of the unknown divided by the rate of N2, okay, squared is equal to the molar mass of N2 divided by the molar mass of the unknown. So we want the molar mass of the unknown gas. That's what we're looking for. Find the molar mass of the unknown gas, okay? All right, so we know that the rate is 0.462. So the rate of the unknown to the rate of N2 is 0.462. So that's going to be 0.462 squared is equal to the molar mass of N2, which we can get from the periodic table, divided by the molar mass of the unknown, okay? So I'm going to go up here. I don't think they worked this one correctly. So the molar, so I'll move this over here and this over here. So I'll multiply by the molar mass of the unknown and divide it by 0.462 squared. So the molar mass of the unknown gas is equal to the molar mass of N2 divided by 0.462 squared. All right, and what is the molar mass of N2? That's going to be 28.02 grams per mole. 28.02 grams per mole. Okay, divided by 0.462 squared, which they actually got correct, but they just didn't put the squared in there when they solved it. So that is equal to 131, okay, grams per mole. Because this rate has no units, so we're still left with our units here. So the molar mass of the unknown gas is 131 grams per mole. See, when they did that, they just left that squared off. So there's an error here. Okay, that's what they did wrong. All right, so find the rate of a fusion of hydrogen gas and krypton gas. Okay. All right. So find the ratio of the rate of a fusion of hydrogen to krypton. So we can't calculate the rate of each, but we can calculate that ratio. Because remember, the rate of H2 to the rate of krypton is equal to the square root of the molar mass of krypton to H2, okay, molar mass of H2, which is equal to the square root of 83.82 grams per mole divided by 2.016, which is H2, grams per mole, which is equal to 6.447. So the rate is 6.4, the ratio of the rate is 6.447. So H2 diffuses 6 times as fast as krypton because it's lighter. Okay, so that completes the problems from chapter 6. So we're going to move on to chapter 12 briefly. I'm probably not going to get very far in chapter 12. All I'm going to discuss today is a little bit of theory. I'm probably not going to work any more problems today, but I do want to go ahead and start on that. So I'll tell you what I'm going to do. I'm going to stop the video and restart the video just so we'll have a division between chapters 6 and 12. Okay, so I'm going to stop recording.